on Tuesday, we talked about gradient dynamics, and what I did on Tuesday, I looked essentially at this situation as a single layer of liquid on a substrate. It could be a droplet, a shallow droplet, and I tried to convince you that it's a nice way to write a thin film equation like gradient dynamics, where you have some energy F that has capillarity, wettability, and you take the variation of this energy, what corresponds to pressure, and you take the derivative of it, get the pressure gradient, multiply by a mobility that was h to the power 3. This gives you the flux, and then the gradient of the flux, as the divergence of the flux is the change in time, the negative sign, right? And we want to go on from this a little bit. And I think you saw this type of formulations popping up through other talks, and Daryl showed how to actually expand this to more general geometries and so on. And it would be nice to see whether one can do this on let's say, on this long wave approximation part. So let me go back here. So that's what we did. So we then, so I had introduced some models, and then I had also shown that the long wave expansion and this gradient dynamics approach sort of are equivalent, but you need the long wave expansion to actually get this Q, right? This was the catch on this method. And then I showed what would be a typical steps in an analysis and illustrated that for de-wetting mechanisms. And so the main form of the equations I had there, I wanted to show you this Cahn-Heer type, what is the thin film equation if your conserved field is H. And then I also mentioned this Elencan type dynamics that could live with the same free energy functional. However, now it's non-conserved field phi, so you just need to write down the variation of f is phi, and then there's some mobility. And one can, for instance, use this to describe evaporation in volatile liquids. Right? So now let's go on from there. What are situations that we can actually not describe by this simple equation for one field? So here I show some rather old experiments from the mid-90s, and here from a review paper by Georg Grausch and Mark Gurkian, where they talk about de-wetting of two-layer films. So what you have a first layer, and then on top a second layer. These are two immiscible liquids, and then both interfaces will evolve, and there will be some coupled dynamics going on. And here on the right, what you can see badly, I think, is a very thick film from here to here. There's a very fine, thin, white line here. That's some I don't know how they actually mark this, the interface between the two films, and this is a cut through the film, and you see some sort of a hole here in the middle that opens, and there are rims that move outwards, and here's a zoom onto this rim. And that's another experiment. So let's not look at these pictures here. Let's just focus on this one. So what this shows is a snapshot, a frozen end snapshot of a de-wetting two-layer film where the upper layer was dissolved. So let's say you have two layers, they start to evolve somehow, you freeze it, and then you dissolve the upper layer and you look at the liquid-liquid interface. And what you see here is that there seems to be a long length scale, like this seems to be something like a cell, this seems to be something like a cell, and then there's a short length scale, right? So in such a situation, you could never get an instability where two length scales show up, right? And it would be interesting to see whether one can see this in a model that takes into account of both interfaces. Now another experiment, same review paper, and I think it was taken from a sequence of papers of Wang and Composto, where people looked at the pattern formation or evolution of very thin films again, but now of mixtures. And these are mixtures that might decompose or might not, and they might de-wet or they might not de-wet. And so you can see in the extreme cases, you can see either a film that remains flat, but the mixture decomposes inside the film, or you could see a film that remains flat, the one that remains homogeneous, but not flat because it de-wets, right? And then you can see all sorts of coupling. And so these are snapshots from the top where you just see the profile evolution in one of those cases. So this shows some coarsening as well. So the A is 1 by 1 micron, and then all the others are 10 by 10 micron, and they are snapshots in time. And this is what people sort of imagine what happens, that on a short time scale, so this is a typical pattern length, a wave vector length, you could say, inverse on a wave number over time. So in the short time scale, you find some evolution of a pattern of a certain wavelength, and then this coarsens. And why this happens, they think that first, in a short time scale, there is a vertical phase separation into two layers, and then there is some lateral structuring going on, like here, holes forming, and then these white parts recede, and you have droplets underneath the layer. However, this is often an artist's impression, because at that time people could not really look inside the films. And if you look at this review paper, normally the models that are made are either saying we look at dewetting and ignore the decomposition, or they look at the decomposition and ignore a little bit the dewetting, right? But coupled models are rare. And there are more crazy situations that I do not want to describe in detail. Here there are some experiments by the group of Robert Margale, also 10, 15 years old, where they have a thin film of a deep block copolymer that somehow dewets the substrate, but in a very curious way, because you find first sort of a phase separation process on this short length scale, and when something happens to this deep block copolymer, so they think some chemistry is also going on, so some droplets evolve and they start to run around, right? And this is really nanoscopic, so these are AFM, these were AFM movies, some of the first ones that were done. And it's actually, I'm not even sure that it's published, because I never really understood what really happens. And this is another one by Peter Müller-Buschbaum, where they actually let a solution of a polymer mixture flow down an incline, right? So I would not advise to do that, because what you see on the long length scale, you see this in the optical microscope, this sort of colored stripes that indicate a long wave modulation of the deposit. And then if you look with the AFM in each of those stripes, you see the different types of local decomposition patterns. So that's, let's say, too complicated. Now, another system that you can't describe with such an equation is, again, dewetting of solutions or suspensions, this time with a volatile solvent. Right? So you have a solution of nanoparticles, for instance, here, gold nanoparticles, of collagen molecules, of some polymer called PAA in, I think, toluene, no, in water. And so what you see in these situations, you would expect maybe a dewetting with very nice holes that grow as round holes as what is used from nice polymer dewetting experiments. But what you see in all these experiments, you see this strong fingering instabilities where you have this richly branched structures. And I will only show here as a teaser, I will not go into detail, a kinetic Monte Carlo simulation that's actually rather primitive, because it assumes only two things. It assumes we have the green stuff that's a liquid, it's allowed to condense and evaporate, nothing else. And we have the black stuff, what are nanoparticles, and they are only allowed to diffuse around on the substrate, and they are only allowed to diffuse where the liquid is, right? They cannot move on the dry substrate. And with this little ingredients, with these few ingredients, there is then one time scale ratio between your condensation evaporation moves and your diffusion moves, and this time scale ratio determines how strong your fingering is, right? So this is it's a fingering that is caused by, let's say, the fact that this front collects the nanoparticles if they cannot diffuse away fast enough. So you get a stratification in the direction away from the hole that also influences the mobility of the entire front. And then you just need a little fluctuation, and this becomes unstable, right? Because with a little fluctuation, you collect different numbers of nanoparticles at, let's say, where the front advances further and where it stays behind a bit. It's like Laplacian growth process, and then you get the instability. So at some point we would like to see this also in some sort of a thin film model, but we don't at the moment. Now, the final experiment that I want to show here at the beginning is a set here that look into the deposition of line patterns from different types of solutions or suspensions. So let's first look at the left side, the left-hand side. So here we have a nanoparticle suspension. These are rather complicated core shell nanoparticles, but this doesn't really matter. This group of Sikun Lin did this with many different combinations, also with polymer solutions. And but these are just the nicest pictures I saw there. So what they have as a geometry, they have a silicon substrate, a glass sphere on top, and then this red stuff is the solution. And they put it in this geometry that's actually for modeling purposes not really ideal, because they want to slow down evaporation, and they do not really want to invest into a chamber that controls humidity and so on. So they just confine it so evaporation is slow, because the vapor cannot really diffuse away easily. And what they find if they take, actually this is light, no it's not, this is AFM I think. So if they look at the substrate down here, they see this very nice regular line patterns. These are concentric rings, but the length scale here is somewhere written. No, not written. So the line, the distance between the line is between, let's say, 1 and 10 micrometers. Right? So whereas the overall geometry is sort of centimetric. Right? So it's really local. These are really nice parallel lines. And then with a little bit of fantasy, you see here in this picture. So this is the motion, direction of motion of the contact line. So normally these stripes are here parallel to this contact line, and here you see a region where they seem to become orthogonal to this contact line, right? And this can be much nicer seen here. So this is taken from a paper by Chi and Fuchs and has been done earlier by Hans Riegler. So these are experiments where a plate is dragged out of a bath of a surfactant solution, an insoluble surfactant. And so this is so-called Langmuir-Blodgett transfer of this surfactant onto the moving plate. And if you then look through the atomic force microscope, then you see this type of patterns depending here on the lateral pressure of this surfactant layer on the bath. But you can also, let's say, just change your dragging speed and you go through the same sequence of patterns. And so you see here lines that are parallel to this contact line here in this sketch this way. Then you see on the other end for higher surface pressure, you see lines that are parallel to the drawing direction, so orthogonal to the contact line. In between you find this interesting letter structure. And here the length scale, this bar is 2 micrometer, right? So it's not, I mean, Len was a bit over-optimistic, I think, with saying nanometer scale. I mean, I'm not sure how far they could go down. I mean, if you really track fast. But what is the shortest that you saw somewhere? 100 nanometer or so? Yeah, probably much smaller. Yeah. Okay, let's first look at the two-layer situation. So, written a bit more formally, we have now a substrate, we have liquid 1, liquid 2, a gas on top. So what we can do, and what we did in also some years ago, you can take the full Navier-Stokes layer 1, Navier-Stokes layer 2, write down boundary conditions for the forces at the liquid-gas, at the liquid-liquid interface, and assume no slip at the solid substrate, include wetting energies and so on, and do the full long-wave expansion, and you come to two-coupled equations of motion for, let's say, we did it at that time in H1 and H2, what is the oral height. However, you can also do it taking the top layer height and the bottom layer height. What is done in the group of Barbara Wagner. They do now a lot of very nice analysis, and Dirk is here, Dirk Peschka, and his neighbor, I always forget the name. You can talk to them about it. So what would you imagine, how do you write down, if you just say, I forget about hydrodynamic, I just want this formulation. So what would you do? How would you write it down? And it's actually very easy, because you just take this equation and you say, okay, now we don't have one film thickness, we have two, so we make it sort of a vector, like a little array, so we make it a vector. And then if you look at this, then we make this a matrix, right? And this would be the most general form you could write down. I mean, I can just say, so because you have one functional F still, right? It's one energy. It should depend now on both film heights. So there are two different variations, and in the most general case, both equations could depend on both variations, right? So I mean, you can have special cases where this matrix Q is then diagonal, and then it would be simpler. But however, it's not the case, because what you have is really this equation. And now I write it in the way the Berlin group writes it. So I write it in H top and H bottom because it looks slightly nicer, actually, than the one written in H1 and H2. You can still write it in this form, but this mobility matrix Q looks a bit more awkward, right? Also, it has the same general properties. Right? So, okay, what do we have? We have the change in time of the two film thicknesses are equal to the gradient of the negative of a flux. So notice I did not put the negative sign out there. Actually, why? How did I write it in the general form? Okay, no, I don't go back. Okay, modulus a sign, but I think it should be right like this. And then you have this variations with respect to H bottom and H top. They appear in both equations, and then we have this matrix of 4 mobility functions, and that look like follows, like the following. So let's look at them. So we have this mobility matrix, and what do we note? The first thing we note, these two are actually equal, so it's a symmetric matrix, and you can actually also prove that it is positive definite. And if you think about the thermodynamics of this type of equation, this corresponds actually to the Onsager relations of non-equilibrium thermodynamics. That is symmetric, and that it's positive definite corresponds to positive entropy production in time. Right? Now, with these properties, you have the dynamics, but again, you cannot just write it down in this general form. You need to get the mobilities. You really need to do the full long wave expansion and so on, or know someone who has done it, right? And energy functional. So it's also very rational how you can construct this. You take capillarity for the bottom, for the liquid 1, liquid 2 interface, what goes with H bottom, and then you take capillarity at the free surface, what is now going in H2, what is the sum of H bottom and H top, right? So these are the gradient terms here. And then you have now, in the general case, we have some wettability energy, but this depends can depend in the most general form on all 3 H bottom, H top, and the sum of them, right? So this would be the interaction of the substrate with the gas phase through both layers, that's that part. The interaction of the substrate with the top layer through the bottom layer, that's this dependence. And the interaction of the bottom layer with the gas phase through the top layer, what's this dependence, right? And if you just write down van der Waals interactions, then you would write down such a expression, but you need to be careful because the A's are not really independent parameters, right? These are Hammer constants, and they depend on the optical indices of the 4 involved materials. So, but these formulas are also sort of, let's say, partly under discussion. One just needs to be a bit careful there. Okay, this is the general form, and I mean it's very nice. And if you look at this again, you see it's again polynomial. So here we have a power 3 of the bottom layer height. We have power 3 of the top layer height. Then we have a square and linear in the film heights, and then we have one that is linear in the other film height and quadratic in the other one, right? So you could just try to write down general polynomials and then somehow discuss away the terms that you don't want. But now, okay, what can we do in terms of analysis? So I just show you 2 examples what one could do. So one can again start with the homogeneous situation, so 2 flat films, and I used here, I think, only long wave interactions, and the change between the different columns here are different ratios of the film heights, but for the same material properties. And so what you see, you can find a varicose mode, so you get the growth rate as I showed before, but now you do not only get the growth rate from the linear stability, you also get the ratio of the amplitudes of the 2 perturbations of the 2 interfaces, right? And it could be positive or negative. And if it's negative, that means where the top interface goes down, the bottom interface goes up, right? So they have an opposite sign. And when this ratio is positive, then where the top interface goes down, then the the bottom interface goes also down, right? And these are then snapshots from the nonlinear evolution, and in this case you would find film rupture of the upper film, and here you would find the film rupture of the lower film. And if you want to look at the long-term evolution, you would need to fix your energy and include short-range repelling terms that sort of stabilize ultra-thin films. And then, however, what you cannot see in this system is that for certain parameters you find actually dispersion relations that have two maxima, and I picked here the one where they're actually of the same height. And what happens there is if you look at the eigenfunctions for this value and for that value, they, in this case, one of them is actually nearly localized at the top interface, the other one at the bottom interface. So you have actually two different modes that mainly affect the two interfaces respectively with different wavelengths, right? And this is from the nonlinear evolution, and you can still guess that this upper interface has a long modulation here that's now modulated in the nonlinear regime by the shorter wave instability of the lower interface. And let's say, I would say it takes some fantasy, but you can, this picture that I showed at the beginning, where there are these two length scale from these experiments, you could say this could be one of these effects, right? But I mean, there are no quantitative comparisons that I'm aware of for any of these systems. So now if you do what I said and you include this short range stabilizing interaction, then you could look at a long time dynamics. So this is also from 2005 or so. So we just did some small scale 1D simulations. Andrzej Potocki did this at that time. And so what you see in after short, so these are snapshots in time now. After a rather short time, you find these little droplets of the top layer sitting on the top layer, the bottom layer. However, at some point, something curious happens because these droplets that swim on top, they pop down and become holes in the bottom layer, right? And then this hole expands, and then here these two droplets, they coarsen still into this one, and then it pops down as well. And so what you do, you see that in the short time evolution, you have a morphologically different solution that you evolved than in the long time evolution. And if you look at the bifurcation diagram now, plotting steady states over let's say the period of this solution. So let's say if I'm here somewhere, then I'm looking at one period here, and if I go somewhere here, I look probably at one period here. Right? So what you see, there are actually two stable branches that overlap in a part. So if you imagine you coarse, and that means you jump along this line, and when you jump from here to there, you need to jump from this type of solution to that type of solution. There are two different types of solution, right? And if you look at the energies, you see there is a crossover. So this would be like a Maxwell point between these two types of solution. So you could follow first this one, and then here at some point, some fluctuations will convince you that you should go down to this other solution, right? And if you have it noise-free, you would still only be able to run to here on the one of the solution, then you would fall down on the other one. Okay, this was the two-layer system. Now let's look at a bit on deposition patterns. Actually, yeah. So there are quite a number of experimental systems where we have such a geometry. So we have some film or droplet that recedes, and then it dumps something, right? So if you start from a hydrodynamic theory, you would say you look into the literature, for instance, at the paper of Omar Matar and Richard Kruster in 2004, and you find this type of solution of equations. So you find coupled system of equations, one for the film height and one for the height average concentration that I show you on the next slide. So the one for the film height, you have one has a conserved part, gradient divergence of a flux, and then one has some evaporation. So the conserved part is the same as before, now written as mobility times pressure gradient. Pressure is Laplace pressure and discharging pressure, so we have wettability, capillarity. And now here we have an evaporation term where the evaporation is not controlled by the diffusion, the gas phase, but by the phase transition at the interface. Right? So it is again driven by the same free energy, so it's driven here by the difference between this pressure and this chemical potential. And this was, for instance, also used by Len in 2001 in a work without the solute, right? Just to study front motion and front stability. Now the second equation oh, I should mention, so the Q, that's the most important element of the model, is actually that we have now a mobility that depends on the film height and on the concentration, because the viscosity we expect to depend strongly on concentration close to the contact line, right? If the concentration gets very high, we actually run into either gelation or we run into a jamming, and the viscosity will actually diverge. So the second equation has this form. So it's written for the product of the vertically averaged concentration and the film height. So this is effectively the local effective height of the solute, right? And we have, it's conserved, so it cannot go off the substrate. So we have just the divergence of flux, and this has an advection term that you can directly relate to the convective flux on the previous slide times the phi, and then there's some diffusion going on. And we have now this expression for viscosity, and we relate diffusion constant via the Einstein relation to viscosity. So this is the so-called Krieger-Doherty law that is supposed to describe particular suspensions, and this exponent nu depends on the properties of your particles, and the literature goes normally values about 2, and if they are spherical, then I think you have 1.7 or so. And you see this is scaled in a way, we scale phi in a way later with phi c, that this diverges at this random close packing, right? Now, the basic phenomena that you can describe is you start, let's say, with a layer that has this solute in, and you let it evaporate and recede. And if you wait till the end, till everything is evaporated, you can see in a small system, you could see typical pictures like that. If you have a very fast evaporation, the layer has no time to recede here from the left, and what you have is essentially a homogeneous deposit with some stuff bumped at the very end, right? Then if you go to very slow evaporation, essentially you remove most of the material to the center, and then the stuff, the solvent evaporates. However, at medium evaporation, you can find a situation where you, for instance, deposit is a single ring, right? So a single ring is not a periodic pattern, so you need to find a region in parameter space where you find a periodic pattern. But before we look at that, let's look at the mechanism for a single ring. So what you have, black is the film height, the dotted line is the phi times h, so that would be the amount of solute, and then the red one is the concentration. And what you see, this front moves slightly, the concentration builds up here, and at that point, when the concentration goes up here, it hits this random close packing, and it arrests the convective motion. However, it does not arrest the evaporation, so it can still move very slowly by evaporation, right? So there are two typical velocities, one of convective motion at the mean concentration and one by evaporation. So moving very slowly by evaporation, you dump the stuff that hindered your motion, and then you start, so it stays behind, and then your front starts again, and then at some point we would hope it starts to develop the next bump, right? So, and this explains why people describe this as a stick-slip motion, because there are just two processes that live on very different time scales. So searching, so thanks to Lubor Frastia, who did the heavy numerics here, it was quite a search in parameter space first to hit the region where we could find things like that, right? Where you find a very nice regular process of line deposition, and then you find surrounding this region, you find all sorts of curious behavior, like single lines. That's also in a wide region of parameter space. But then there are fine regions where you can find a finite number of lines and then a homogeneous deposition, or either this numerically very. I mean, this depends very strongly on numerical details. So this is like an intermittent deposition. So this indicates that the system is slightly chaotic there. Now, if you look at the phase diagram, you can plot, for instance, the mean concentration at the beginning and the evaporation rate, and you find this large green region where you have a regular line deposition, right? And then you have the region surrounding it, the white one, where you have a single line, and then there are these special regions with finite number of lines and so on, right? So that was very nice, but then you would say, okay, what type of physics does this have? I mean, this has only one active ingredient. What is this strong dependence of the viscosity on the concentration. And if you now say, but you said just gelling. I mean, gelling is not just jamming, right? So you would not need more physics in. You need maybe a decomposition of a high concentration region, the low concentration region. You would like to study how does the process depend on the influence the solute has on the wettability, and you could start to sort of fiddle with these hydrodynamic equations and try to get other terms in, and people did that. But we tried to do this more systematically. But before I show you this, oh no, we skipped that. I have this again later on. So what we want to do, we want to take these hydrodynamic equations and we want to reformulate it as well in such a form with a proper choice of the two fields and with a proper choice of that matrix. Because if we are able to do that, we can then start to fiddle around just with the energy functional and put all the physics in that we know from equilibrium and then get automatically sets of equations, and then we can check whether these are identical to the ones we have in literature. So before we do that, I want to show you how you would write the standard diffusion equation as a gradient dynamics. So again, we want the diffusion equation in this form. So phi is now a concentration in 3D space, let's say. And so we want the proper energy function f there. And you could, I mean, if you visualize the diffusion equation, it's just dt phi equals the Laplace of phi. So you could say, oh, that's easy. You just choose phi square there, right? And then have a constant here. But that's not really a free energy function that you would recognize from physics, right? So what you should do, you should write down the energy functional that just has an entropic term, phi log phi, that just assumes you have a low concentration solute in your film, right? That's the free energy you would write down. And then you need to decide what is the Q you have to pick to recover the diffusion equation, right? And what you have to pick a linear term in phi. So you would say d tilde is a molecular mobility times phi gives me this mobility here. And if I plug in this free energy functional, I exactly recover the diffusion equation. dt phi equals d Laplace phi, where d is now defined as d tilde times kt over some molecular length k to the power 3. Right? And this is also the starting point. This type of formulation is the starting point, for instance, for dynamical density functional theory, where then you just make this functional arbitrarily complicated as you get it from thermodynamics, and you get automatically a dynamic equation out for this, right? Now this gives us a hint what we want, because we know we have in the hydrodynamic equations, this was in the low concentration limit. So we want such a term in our functional here. And as we write down an energy per substrate area, we have to take such a term and multiply it by h, right? Now, but there is a trap here, because this phi here is really a conserved quantity, because it's a phi, a concentration in 3D space, right? However, what was the phi? How did I introduce this phi in this equation? I said this phi is a vertically averaged concentration, right? So that's not a nice variable, because actually if I keep locally the amount of solute constant, but I change the film height by adding some solvent, I actually also change the phi, right? So phi and h are not two independent variables. I cannot vary with respect to these two variables, right? And I tried for some time to get equations doing that, and nothing good came out of that. So what one has to do, one has to decide that what is this second field, I call it here psi, that is independent of h. So that is the actual mass, the local mass of the solute. So h times phi, right? So the moment we decided for this to go for a formulation in h and psi, and actually the hydrodynamic equation hinted at that because it was written as dt of phi times h, right? So one should actually have just seen it. So if you do it like that, this is the conserved part, and then this should cover evaporation, right? So this would be a non-conserved part. So, and what happens, I show you on the next slide, I show you the Q's and the F, and then you, if you choose the one that I have on the next slide, you exactly recover the hydrodynamic equations, with one exception. You get an additional term in the evaporation term that was missed in the other approach, because you get a dependence of the evaporation on the osmotic pressure in the film. What actually on physical grounds you would expect. And there are also models where people try to include this by hand by making really sort of ad hoc changes in the evaporation rate depending on concentration. And here it comes out automatically. What is the Q? The Q looks rather familiar, right? From the two-layer formulation, we have an h to the power 3 here. We have a quadratic times a linear here. It's symmetric as it should be. Here we have a linear times a quadratic. And what we don't have a psi cube here, what we had in the two-layer form, but all the rest here looks the same. And now we have this d tilde here, what stands for the diffusion part, right? So you could imagine this is a mobility that is the sum of a convective mobility matrix and a diffusive mobility matrix, right? So this plus 3 d tilde psi here gives us the diffusion part. And we use this free energy, so we have the gradient term as before, we have the wettability term as before, and then I call this G, where in the simplest case we say G is our phi log phi in the entropic part, but the catch is we have now to write it as psi over h, right? And the moment you write that down and you see, oh, my variations with respect to h will actually get very nasty terms from here, you give up the first time, right? Because I mean, I couldn't imagine it comes to the right result, but actually if you take it through all the terms that you don't really like, for this choice of mobilities, they just compensate, right? So they just go away. So that's you can also make a more detailed comparison to the hydrodynamic form, and you see this also falls into place and actually consistent with the fact that osmotic pressure does not contribute in the bulk, right? If you have a concentration gradient in the bulk, you do not get a flux, a hydrodynamic flux due to osmotic pressure. So this is all consistent. And now the nice thing is that having this form, we can say, what happens if our G is not just the entropic part? If we have an energy function that allows for decomposition also, then we just plug it in here, we go through the equations, we write down this, and we can recover sort of the hydrodynamic form of the equation and compare to what there is in the literature. And what normally happens is that the literature models have terms that you get, but they do not have all the terms, right? So I mean, my impression is that if you started on the hydrodynamic level, you do not get all the terms, because you can actually not really imagine what you have to add. So so the simplest example would be we want weakly interacting colloidal particles, so we would additionally to the entropic term, you would say a minus b, where b is a positive constant, times phi squared, so this would be weak abstraction. And if you now say, okay, but if this becomes too strong, then they will decompose and you will actually find a blow up in your system, right? Because you do not limit the gradient in the concentration. So what you then say, okay, let's put the Cahn-Heert free energy into our free energy. So we have such a double well potential, for instance, and we have now to put a gradient term in the concentration, and you see this will get really nasty because this is now gradient of psi over h, right? And so this gives you some bulky equations, but then you go into literature, you find this work by Narey and Tifo, where it took them 10 pages of asymptotics to get the long wave limit of model H that several speakers mentioned. And you get exactly the same equation with a tiny difference that actually hints at the problem in model H itself. So that was actually quite convincing. Now, something that people like to do is they like to think about a wettability that depends on film height and also on the concentration in the film, right? You can imagine if your solute has, as a film itself, imagine as a liquid film, it had a different contact angle than the solvent, then it should somehow change wettability. Now, if you put this in, what you get a convective flux that looks like this. So you have Laplace pressure term, you have the discharging pressure term that now depends on h and phi. That's what people normally do. They replace the discharging pressure that depends on h by something that also depends on phi. However, I never saw this type of term that automatically comes out. So what is this? This is an additional part to the convective flux. It's a bit like a Marangoni flux that comes from surface tension gradients. However, it's not a Marangoni flux because it's living in the bulk, but it only lives in the bulk if you're close enough to, if the free interface is close enough to the substrate. Right? So it's a sort of an equivalent thing to a Marangoni flux, but for ultra-thin films close to a solid substrate. And then if you change the energetics, you should change all the channels of transport. So not only convection, also diffusion changes automatically. Right? So you get an additional term in the diffusion flux. So now if you do this, now let's not go through the gory details, but if you assume you have a mixture, and this is work done with Desislava Todorova, if you have a mixture and now we have a non-volatile film on a solid substrate, you can now say, okay, let's assume we get our Hamager constant from the book by Israel Achvili, where you can find how they depend on the optical indices and the dielectric constants. And we now say, however, for the film, so we have the medium 1 and 2, however, medium 3 is now a mixture. So this should depend on phi, and we use homogenization techniques to actually get those. And then we get disappointed because they look like straight lines, essentially over the concentration from 0 to 1 here of PMM, wait, what is it, for silicon oxide particle in PMMA, no wait, sorry, silicon oxide is a substrate, then we have a mixture of PMMA and PS, and this is air, and this is the concentration, I think, of the PS in the PMMA, and you see it's just linear, right? So, and this happened to many of the cases where we had. So we assume a linear dependence of our A in the Hamager constant. And I just showed you one example where we have a situation where the pure solvent film would be absolutely stable, no dewetting. Then a pure solute film would also be absolutely stable. So Hamager constants for each of them would be stable. Then there would be no bulk solute solvent decomposition. So we do not even include any attractive interaction between the two. However, if you put all this together, it will still dewet, right? Because the two modes, the two fluctuation modes of film height, of composition, they couple. And so you can imagine if you have a flat homogeneous film, it cannot decrease its energy by staying homogeneous and becoming wavy. It can neither decrease its energy by staying flat and changing its composition, but it can decrease energy by modulating its composition and its film height at the same time. Let's say moving all the solute into the drop states or moving all the droplets into the thinner states, right? And if you look at, so this M1 is an important parameter. It's the change, where is it written? Here. It's the change of this, the linear change of this Hamager constant. So here we would expect, for positive M1, we would expect at some value like 3 or 4, the film becomes unstable if you assume it remains homogeneous. However, if it does not need to remain homogeneous, it becomes already unstable for a lower value of this M1. That's not very amazing, but what is amazing that it becomes unstable even when this M1 is negative, when you would actually expect it stabilizing, right? But it's not, because you can move stuff around. And this is M2 is an important parameter that gives you like the strength of diffusion as compared to the molecular interactions that are responsible for wettability, right? So if diffusion of your solute is sufficiently slow, then you get unstable. And these are some nonlinear states, steady states that you can find. So you have a modulation in the film height. Look at the green line here, and in this case, the concentration is higher in the higher state, and it's lower in the lower state. Okay, so that was not the end. I split in 3 lectures, so we are sort of in time. So I showed you experiments with film and drops of mixtures, solutions, suspensions, either volatile, solvent or not. And I tried to convince you that we can write down a nice gradient dynamics approach for 2-layer films, and one that looks at actually rather similar as well for mixtures, right? And this now allows us to actually essentially create sets of models that are intrinsically consistent. I mean, you can always argue, shouldn't you change the mobility as well if you change the energetics? But often I think you can, in the first approximation, assume this remains the same. But you will need, let's say, also people that do the long wave approximations to check in all sorts of limiting cases whether you will recover the correct mobilities, right? And I do not talk about it, but we published last October a paper where we did the same for insoluble surfactants, right? So you can write down an energy for this insoluble surfactant case and then two coupled equations for the surfactant concentration and the film height evolution, and they are in the same form, and the mobilities actually look nearly the same. They just have, instead of a factor 1/3, they have, I think, a 1/2 here and a 1/2 there. Also, but let's say it might be slightly different. Okay, so what do we want to do next? So now I said I want to talk a little bit about these gradient dynamics formulations, but I do not want to go on with that. So now I want to show you some effects that occur in quite a number of different systems. So I want to talk about depinning transitions and actually bring the deposition patterns also in the context of a depinning transition. Now, let's look at some of the experiments again. So I had shown already in the first lecture this plot where we had a capillary rise of a meniscus in a little capillary, in a capillary tube, and we saw, so rise would be it's going down here, and we saw it's not a nice exponential, but it's this rect form here, this rect form, and like a stick-slip motion. And people think that's also related to heterogeneities of the substrate, and the people think that also these heterogeneities are related to so-called contact angle hysteresis, where you see different contact angles in the limit of zero speed. If you advance a contact line and you advance it slower and slower, you will come to this type of limiting point. And if you let the contact line recede and you let it recede slower and slower, you come to this limiting point, right? So this is the so-called, this is the so-called contact angle hysteresis, and again it's thought to depend mainly on substrate heterogeneities. Now, I think you saw these pictures because Luca Beffarale showed this as one example of lattice-Boltzmann calculation. So I was very glad when I found that preprint a month ago or so, because I think it's the first experiment where people really put a droplet on a regularly patterned substrate and really measure things like mean velocity over driving force, and essentially investigate this deepening transition we were interested in already some years ago. So this is a plot where they just condense water on this heterogeneous substrate, and the size of the droplets that's different on the different stripes indicates there is a different contact angle. And then this is a side view, so we have this droplet sliding down, and these are positions of the contact line, and you see the stick, slip, stick, slip, stick, slip, and so on, right? And these are plots of the speed, the non-dimensional speed of the droplets over the distance to the critical bond number, what is essentially the driving force by gravity. And you note here that they draw straight lines here, and I will tell you in some minutes that it should be power laws with a power 1/2. But it might be that this is only visible if you go very close to the concept. Okay, let's skip that one. We had this already. So we had this deposition patterns. I fancy that paper. It's from 2005 from a Japanese group, and they have a different geometry. So in the experiments by Sikun Lin, we had this meniscus between the sphere and the flat plate that receded sort of passively, right, just by evaporation. And here now they have a meniscus between the class plate and the second class plate in the they have a controlled speed of this upper class plate, right? So that means they uncover the meniscus at a predetermined speed, and so they, in some sense, they force evaporation, the overall evaporation to be at the same speed, right? And then depending on the speed and on the concentration of the solute, they find the nice and maybe boring parallel line pattern, so parallel to this receding contact line. Then they find what you can't see here well, but here you see in the AFM picture, they find actually hexagonal arrays of spots. And they find these ladder structures that we also saw for the Langmuir-Blodgett transfer. So this all seems to be rather generic, and we would like to get models to study them. Right? So now let's first look at the most simple deep pinning problem. Simple liquid. Now we use this equation without the vector bars here. And the only difference to the equation I showed before is that now our wettability depends not only on film height, but also on space. Right? So we can impose a nice regular patterning. And here I just put an abstract driving force. This could be gravity down an incline. It could be a wettability gradient. In the examples I showed, this will be a gravity on an incline. Right? And now we assume we have a heterogeneous substrate where we have hydrophobic patches and hydrophilic patches. And we want to see how the solution behavior of the equation changes when we incline this further. Right? And just note that a very similar equation describes drop on a rotating cylinder, and there we expect very similar transitions. Actually, one sees them there. And the nice thing about this system is it's really periodic. So whereas we are always cheating a bit by saying we extend our system periodically, right? So what flows out at the bottom flows in at the top again. That might actually lead to spurious solutions in some special situations. So if you look at this rotating cylinder, then you can avoid all that. The price you pay is that then you're confined to the sinusoidal heterogeneity, what is gravity going either down or, let's say, if you sit on the cylinder, going up to your feet or up to your head. Okay, some details. So here we use this discharging pressure, what combined this long-range power law and this short-range polar thing that Ashutosh Sharma used it very often, and Len mentioned it as well. And then for the heterogeneity, we use this rather awful Jacobi sign functions, because we could switch them by just changing this parameter little k from a sinusoidal modulation to a modulation that had, let's say, individual peaks, like looking like a Gaussian more or less, but being periodic on a longer period. Right? That's the only reason why we use that. Important is the epsilon. It's not a small parameter. So if epsilon is smaller 0, we have a hydrophilic defect in a hydrophobic background, and if it's larger 0, it's the other way around. Now, typical results for rather tiny droplets, but here we can see the bifurcation diagrams nicer. So what we have here is a hydrophilic defect. Here's a hydrophobic defect. So this one keeps the droplet at the back if I incline in this direction. So this wants to keep the tail of the droplet, and this one wants to block the front of the droplet. Right? So the more I incline, the longer this droplet becomes, and the steeper this droplet becomes, because it's pressed against the defect. And these are all steady-state solutions, right? Stable, steady-state solutions. Right? However, you see here the last line is actually as a rather odd value of mu, and here this by chance it's actually a round value, but this is the last value of mu I can get a steady state, right? It is stable. Why? Because if I look at the bifurcation diagram, it looks like this. So what I have here mu as a control parameter. Here I have a solution measure that is the norm of my solution, and these here are the droplets when they are pinned by this hydrophilic defect at the back. So these are steady droplets. However, here is a saddle node bifurcation. These are all unstable solutions that should be drawn with dashed lines to make this clear. And so if you run a time simulation somewhere here, you go to this dots there, right? However, if you run it somewhere here, something different happens. So what you see is droplets. So here's a space-time plot. So you have droplets that, in this case, on a long time scale, they just stretch. They get very slowly, they get longer. And then on this 5 slices here, something rapidly happens, because the drop sort of snaps off the defect at the back and it moves to the next defect, right? So this would be a stretch slip motion, right? And if you look at the similar diagram for the hydrophobic defect, you really see a stick slip motion. And they are periodic in space because this is imposed, and they are now also periodic in time. So these are time periodic states, and the closer you go to the bifurcation point here, the larger the discrepancy between the time scale of the sticking and the slipping becomes. And you would see this as a stick-slip motion. With your bare eye, you would actually not see it still moving. Right? And so now if you plot the averaged speed, I plotted here as 1 over the period in time, over the distance or over mu. So if you put this into a log plot over the distance to this bifurcation point, you see a nice straight line with a slope 1/2, what indicates that this is a power law that exactly corresponds to the one you find for a global bifurcation called the Sniper or settle node infinite period bifurcation. Right? So if you go around the settle node, you see an eigenmode changing sign, but that's the one that is related to this transition from this stable solution to this unstable one. You do not see any complex eigenmode changing sign of the real part, or so indicating there is something time periodic going on. You can't see that in a bifurcation analysis. That's a global bifurcation. Right? Now, the same happens in 3D. So 2D thin film equation. I just showed this because there's always this question whether the 1D result is relevant for the 2D situation and the other way around. And in this case, it exactly the same happens. So you see steady states, unstable steady states, and here this time periodic states, and here this is now a log plot, and you see this power law 1/2. So again, it's a Sniper bifurcation, and you see this is now steady droplets that you can also study using these continuation methods, and this is the evolution in time. And if you can read these little numbers here, you see that what do you see? You see that from here. You see, how do we look at this? No, it's actually difficult to see. So what I want to see is that the time where it actually moves between this line where the defect is and the next line is long as compared to the time it sticks around the defect. But actually that's not really well visible because we would need another snapshot in the middle that shows that. Okay, so this is the depinning in the simplest case, and I just want, if you really like very complicated bifurcation diagrams, then what you would like is another work we published last year where we said, okay, we have the 1D picture, and the 1D droplets are actually ridges in 2D, right? Then we have the 2D picture where we have droplets that depin. So if we have ridges and droplets, then we have Rayleigh plateau instabilities between the ridges when they decay into droplets. Now we have also depinning instabilities. And so if you add the second control parameter, like the lateral size of the system, you just, depending on that size, you get the most crazy transitions between, let's say, the 4 or 5 states that we have looked at. Right? But I don't want to show that. Now let's mention something Daniel mainly did. Where's Daniel? There. So in Göttingen, so the aim was to look at essentially a very similar situation, but now not be restricted to small contact angles, right? So it's always a good, let's say, sanity check to have at points to see that also for larger contact angles you see actually similar phenomena. And so what Daniel looked at is this situation where you have, let's say, a modulation on a wavelength, so invertibility that is actually shorter than the droplet, right? So this droplet would cover several of these stripes. So this is actually rather close to Lucas' experiments, right, where also the droplet was put on several of those stripes. And now these are no full, these are Stokes calculations where you have to assume a slip length that actually control, you could say, the speed of the droplets, right? And the slip length, the drawback is that it has to be rather large. If Daniel agrees, but that's the usual problem. Right? So, and I just show you some results, and that are actually rather interesting. So we have here the driving force, and here the solution measure is the base length of the droplet, right? It doesn't really matter what we plot here. So we have the steady, stable solutions, the steady, unstable solutions, very similar as before. And now look at these dots here that are for a rather small slip lengths. And you see these seem to come out of a sniper bifurcation, but here we cannot go close enough to the bifurcation point to really see the power law. However, what we also see here, it's actually more, well, if you change the slip length, you can actually see that this bifurcation walks along this unstable branch, so they seem to end here. So what is this? So there is another global bifurcation that actually ends at unstable steady states. That's a so-called homoclinic bifurcation. And there are now two ways how you could experimentally distinguish between this one and that one. One is the law how the period changes, the speed changes close to the bifurcation point. So here it's a power law of 1/2, here it's logarithmic. But I guess it's probably an illusion to really see this in the experiment. However, there's another way, because you can just say, if it's a sniper, there's no hysteresis between a steady state and a moving droplet, right? Independent what is your initial condition, you always get here moving, here sticking, right? However, if you have, let's say, the triangles here, then there is an entire range between here and there, where depending on how you start, you either see a steady droplet or stick-slipping droplet. Now we try to find, we try to convince Luca, I think, to find that in the experiment. Now this was two ways of doing stick-slipping droplets, and I think it's quite convincing that you see the similar effects in the long wave and in the full Stokes calculations. And I should mention, we also saw the homoclinic bifurcation in some of these crazy bifurcation diagrams I mentioned. So we want to investigate it a bit further, actually. So let me check. 20 minutes, right? Yeah. Yeah, I think I will talk about this one. So now let's look at a rather different system. And I do this to sort of convince you that if you have certain, let's say, basic structures of equations, certain basic features of your energies that you can say, let's say, one, for instance, for droplets, there's some force that keeps the droplet together, and there's another force that tries to spread it out, right? So if I have, for instance, a distribution of nanoparticles in a heterogeneous pore, then there might be some force like entropy that tries to spread this distribution of the particles out, and there might be some interaction between the particles that tries to keep them together. Now we have a heterogeneity in this substrate, and if we add a driving force, not an oscillatory one like drawn here, but let's say a DC driving, then we would expect maybe very similar phenomena, right? Now particle distributions that either pinned to this heterogeneity or particle distributions that move through the system. Okay, so I told you already all the results. So what is the equation? So the equation, you see it becomes slowly boring, is just the same we had before, right? So we have the evolution equation for a conserved order parameter field. However, this is now really derived from heavy thermodynamics for equilibrium functions here that really describe particles that interact and have a hard core as well, right? So this is work with Andy Archer and Andrzej Potoczky, and Andy, I think, is the main responsible for really getting those functionals. And then you plug in the same Q as before, so for the diffusion equation. So this is a linear dependence on rho. So you recover the diffusion equation in the limit of, in the dilute limit without interactions, then just this entropic term gives you everything. And now what do we have? We have an effective interaction with a substrate, so with a pore, so this would be the heterogeneity, and we also put the driving force in here. Actually, as we use something like a potential energy, we can actually really write it into driving force, but that's something I have on my Outlook as well. Then we have an attractive force F that is essentially an exponential attraction, so with an exponential tail. And then we have a hardcore repulsion, and I show you this is actually the awful part of the integral. So let me go down here. So let's start from the bottom because this is the worst. So this hardcore repulsion introduces a parameter h, what is like a particle size, right? So they cannot come closer than h. And it looks first a bit harmless because it's just a single integral, but then hidden in this eta, where's eta? Eta is here, and wait. And here's this phi of rho. So rho is the density, depends on eta, and eta itself is again an integral over a particle size, right? So this makes it's quite awful and makes that the final equation is actually still an integral differential equation. So it's not a PDE. And then we have this attractive force where here's the important parameters alpha, what is the attraction strength, and then there's lambda, what is like a typical length scale for the attraction. So now how can we compare this to droplets? So okay, this is our sinusoidal modulation of the external potential. This is our driving force, external driving. Let's fix this to 1 for what I show you. And then we have this thing that brings the particles together. That's like the destabilizing van der Waals interaction for the droplet. It tries to keep the droplets together. Here it tries to keep the distributions together, right? And entropy tries to make it spread. Now, let me show you a typical result. So here we fix actually the driving strengths, and Andre is at the moment working on actually going now back to the static situation, really first understand all the bifurcation diagrams there, to then understand better what we see here. So what we have here as a control parameter is alpha, what is this attraction strength, right? So the larger we go here, the closer this distribution wants to be together, right? So if they are widespread, there is just a steady state here where most of the particles are sort of distributed. They are distributed in the different potential wells that we look at. Let's say we look here at 3 potential wells in a system. And then at some point you find this type of a solution, what is a steady state, where now all the particles try to be in one of the potential wells, right? So that's like a coarsening of droplets. However, in between, so you have an unstable branch here, and in between there is a curious branch that are actually time periodic states, where this distribution travels from potential minimum to potential minimum. That's like our stick slipping droplets, right? And it ends on one side in Hopf bifurcation, on the other side in one of those homoclinic bifurcations we had before. And because it's late and we are tired, I want to show you 1 or 2 movies to keep you watching for another 10 minutes. So this is a movie of this on this time periodic branch. So it's not very exciting, so I don't want to overload you. So what you see here is really the particle distribution, and now the forcing is in this direction to the left. And what you see here, if you focus on this one, this goes down, this goes up, then this goes down, and this goes up. So it's actually not that the distribution slides as one block. It's really, there's like a surface wave going on top. So one could say this is a depinning via a volume mode of mass transfer, whereas in the droplet it was a depinning of the translational mode of this droplet motion, right? And now that I have prepared you for movies, I can first show you this one, because it's a bit more exciting. So now we introduce actually this hardcore repulsion between that was not in the previous movie. And what you see here, you have actually a blob of, in this case, these are 4 particles, and they move through the system like a block. But what is actually curious, that when they, whenever they are over this potential minimum, they look more like peaked, what actually means it's like a local crystal, right? And then it melts when it goes over the well, then it is crystal again. And so this is actually rather cute. Also from I just show you the previous slide, when I can go back here, if I can go back. I never find out how to go back again. So in the similar diagram I showed you before for h equals 0, now we have this hardcore repelling now over alpha. If you look just at this set of equations, so this is h 0.2, and you see it looks already rather wild, and if you zoom into this region here, you see actually there's much more. So there are several traveling states, and so there is some interaction between a transition of, you can have a melting of this local crystal, and you can have a moving, and that's why I thought we should now first go back and actually understand the equilibrium better, and then come back to this later. Now, it's not yet the end. I'm teasing you. So we talked about this depinning now, and I showed you briefly that if I do drops and ridges on a heterogeneous substrate, I have certain features of the depinning transition. So, and I introduced the sniper bifurcation, the homoclinic bifurcation. And now I did the same for these interacting particles. And again, there I showed you a hop with the homoclinic bifurcation. So there seemed to be overall a picture that, I mean, you find these three types of bifurcations. You could actually catalog all the experimental systems you have, and let's say distinguish them by the 2 or 3 distinctive features of these bifurcations and sort of try to make a catalog. So at some point we also noticed that the depinning patterns that I showed you already, so I showed you this one, but what I didn't show you is that we can now make a nice cut through this diagram, either keeping evaporation rate fixed and changing concentration, or the other way around, and we can look at solutions now changing concentration. So this was going from top to bottom. So this would be, or from bottom to top actually. So this is low concentration, this is high concentration. These are just the final periodic states. So however, if we can now analyze them, we see actually there is an amplitude and there's a period that are the most important measures. And we see if we go to a small concentration, we actually see the amplitude of these peaks, it remains rather the same. However, the period seems to diverge. Right? So if you think about this in terms of a bifurcation, then what it has to be some global bifurcation, right? Because this period diverges. However, on the other side, the amplitude seems to go to small values. It's still finite here, and the period seems to go to a constant. It's small compared to these large ones here. So this would indicate this is either a sub or supercritical Hopf bifurcation, right? However, in this complicated system, we actually cannot really analyze this in detail. We can't access it. So then we thought, okay, haven't we seen this other system where we had this Langmuir-Blodgett transfer? And then there were all these people in Münster that had developed a very nice thin film theory. So mainly, wait. Where are they? Michael Köpf's PhD was this. So what they have a meniscus, let's say, of water, and then they have the surfactant on top, and they drag out this plate, right? And we had again this line deposition, right? Now of this surfactant on this plate. And they wrote down coupled system of equations for the surfactant concentration and for the film height, where hidden in this pressure here, there is the full thermodynamics of the surfactant, right? Because there can be actually in the pressure and in this term as well, where you can have actually phase separation between 2 different phases of the surfactant, and this can be triggered by the distance to the substrate, what makes it even more complicated. And then so you can bring this set of equations, you can bring with a small amendment into this nice matrix form, so it fits into this surfactant models. And so Michael, he had actually 2D simulations for the line pattern. So this is actually snapshots in time of a single simulation, where on a short time scale it would develop stripes that are parallel to the contact line, right? So this would be the most dangerous instability mode. However, in the long time scale, these would actually flip and become stripes orthogonal to the contact line. Right? However, again, the same problem as in our deposition studies, you cannot do a proper bifurcation modeling on this system. So we came together and thought about what is the most primitive model that one could invent that still captures these processes. And what we came up with is a Canhea type model. So we say assume that there's just some concentration C, and it can have a phase separation. So it can it can have a phase separation. So there's some first order phase transition. You see it here. There's a C cube and the linear term in C. And however, we say this effect that the substrate, the distance to the substrate, actually influences the thermodynamics. We put in a prefactor in this linear term that now depends on x. So we say we drag this field C that we pin on some boundary, we drag it over threshold, right? And this is a tracking speed. So you could say, okay, this is boring. This is just the co-moving frame. So why don't you go into the co-moving frame? So we can't, because by the boundary conditions we select the frame, right? So that's, in that sense, it's the most simplest dragging that you can have, right? So that's a step. Now for this one, we can actually now do a bit of continuation for the steady state solutions. And what you get is this very interesting wiggling curve. So what do we see? This is the norm of the solutions. This is the dragging speed. And if we drag very fast, like here, these are steady states that look like these here. So we drag to the right. So we drag out a low concentration state. If we are here, we have a steady state. So we drag out a high concentration state. But that's steady, right? So we deposit a homogeneous layer. And then all these are all unstable, but still interesting. So they are these solutions with different numbers of bumps. So this might remind you Edgar's talk, right? Where he talked a lot about homoclinic snaking. So as a very loose way, saying this is sort of not a very clean, but a dirty heteroclinic solution going between some fixed point that is here ill-defined, right? It's a boundary point to a fixed point. So this would be heteroclinic snaking of some solutions, right? Now, what happens if you go beyond that point? So these are our steady states. So if you run time simulations starting from a homogeneous state, what you actually do beyond this point, you fall on this line of blue crosses that are actually now time periodic states, right? And time periodic states means it's actually lines that are dragged out of the system, right? So these are these deposition patterns, these line patterns, and they come out here in a homoclinic bifurcation, and they end here in a Hopf bifurcation. However, they are around here. There are actually 5 Hopf bifurcations, so that's why this is so messy here, because there are many interacting modes. So I can't show you the picture yet, but now we can also follow all the time periodic branches that exist here. We can follow them by continuation, and there are 26 of them. And it's too messy, let's say. But what I want to say is that I expect that, the behavior for all these other deposition patterns, will be governed by rather similar, let's say, bifurcation structure behind. And now I think I did not yet tell you why I put the depinning of the droplet and the deposition patterns into the same talk, right? So, I said, okay, they have the same type of bifurcations between steady states and time periodic states. But this is not enough to say they are sort of similar. But now if you imagine the system of this receding front where you deposit at some point the line patterns. If you put yourself into the co-moving frame with a front, right? If there is a homogeneous deposition, what you have a solution of the concentration field that is not homogeneous. It changes in space, but it will have a little bump at the moving front. And this bump will move with the front, right? But the moment you deposit lines, then this bump actually depins from the front. It stays behind, right? So in this sense, it's a depinning transition. And the same, it's clearer here, because here the meniscus is pinned by the boundary conditions. And the moment you go to this blue crosses, you actually really depin this periodic solution from the boundary. It then moves with a plate. So in that sense, they are all depinning transitions. I think one can classify them in a similar way. So, summary. So the last half an hour, I talked about some experiments with deepening droplets and line deposition, and then I showed you example of bifurcation studies. And let's say each of them is interesting in itself, but for me they become more interesting by looking at them all together and seeing what is similar, what is different, and so on. And I tried to tell you about some results for the line deposition, and there I think there's still some work to be done to, for instance, there's no bifurcation studies for the 2D situation, where you have a lot of very crazy actually patterns. Now, a general outlook, I just put up some random words essentially. So we have this gradient dynamics where, I think it's very powerful, and one could try to get more of these thin film systems into this scheme. So what are the important issues? So for instance, the evaporation models. I mean, there's a lot of discussion about different types of evaporation models. It would be interesting which of them you can actually include in this formulation and which one sort of do not really fit into this framework, right? Because the question is, do you need to include latent heat effects? Do you need to include temperature and so on? Then I would like to have a formulation for soluble surfactants. Then you would need a 3-field approach. So you would need to make this vector consisting of 3 fields and then have all the cross fluxes as well. Now the question is, driven systems. I sneaked the driven system in towards the end by having this deepening droplets and the driven particle distributions. Now the question is, can one put them into this gradient dynamics form? And you can, if your energy is a potential energy, for instance, like for the droplet on the incline, you can put it into the same formulation. But if you have other driving forces, you will not be able to do this anymore. And then so this to explore further this relation to DDFT and maybe couple thin film approaches with some DDFT stuff would be interesting. And then deepening transitions are possibly still interesting. Okay, thank you.
Any questions for Uwe? Andrew.
So you mentioned the difference between the homoclinic and the hop as ways these droplets depin. Now, do you have any feeling for what is that telling something about the physics that's changing these different transitions? Because you've got a big difference between essentially an infinite period at onset compared to finite period.
I mean, first, I think if you have a macroscopic droplet depinning on a heterogeneous substrate, you will not see a hop, because the hop essentially is driving by the flux through the precursor film. But it's tiny. I mean, we saw it in the thin film model, but I mean, these were, let's say, droplets 3 nanometers high and with a 1 nanometer precursor film. So that's not realistic at all. And then you would also need different driving forces. So in that sense, I mean, it will be depending or will be sniper or homoclinic in the real systems. But for the thing in the nanopore, I mean, there you can imagine this type of transitions, right? And I mean, there is this issue, the Hopf bifurcation. One thinks that it first starts to oscillate locally, right? And then it needs still a global bifurcation to go and move on the big period to the next. So I mean, that's an open question, and I think we can attack this the moment we have this continuation codes for the time periodic states really going in a stable way. Then we can see what happens there, because all the papers from 2006, all the time periodic states are done with time simulations, and there are pieces missing because they also go around certain nodes, and then we can't follow them anymore, right? So, but then, yeah, I mean, these are interesting questions. And
I was also interested in the homoclinic to sniper transition, particularly with that Stokes simulation.
Yeah.
Because you can, I may be wrong, but of course one can think of it as that you were going, when you've got the homoclinic, you come in at finite period. Because you fall, as you increase the parameter, you fall off the end, so you do actually see a finite period, corresponding to the fact that you've got a finite slip length that you've introduced. Now, as you reduce this slip length so formally it can't move, you're going to the sniper that you would never actually see in finite time.
Or you mean if you go along the steady state and then fall off, then it's finite, because at the bifurcation it's still infinite.
Right.
Yeah.
You don't see that with the sniper, and I wonder if that's related, can be related directly to this slip length that you're introducing.
I don't know. I mean, when we actually saw it, there was this discussion whether it's actually possible to have at the same parameter values steady state and the moving droplet, because where would the energy be stored, let's say, when it goes over a defect? Because there's no inertia, right? So there's no kinetic energy per definition. But then we realized that actually the energy is stored in the interfacial profile. So the interfacial energy takes the role of kinetic energy and allows actually this coexistence in the parameter space. So
I have shown experiments where we have that behavior.
Yeah.
Any further questions? Thank you. Thank Uwe again.